Can you guys see my screen?
Yes, sir.
Yes.
Okay. So today we're going to do reading six. Uh, it's on simulation methods in finance and how to model uncertainty. We are also going to implement a technique called as Monte Carlo simulation today to see how it looks in Excel and what could be the applications of the same. Very important technique to model future uncertainties or to model scenarios which probably have never occurred in the historical past. Okay, so we'll look at some applications later on as we go. So this chapter is going to cover concepts related to log normal distributions, Monte Carlo simulation, and bootstrap resampling. We'll first try to understand these terms and then we will implement Monte Carlo simulations. Okay, so the first premise is why asset classes can't be normal, right? So when you look at an asset price and when you look at a normal distribution on the left, can I say an asset price can never fall below zero? An asset value cannot be negative, right? Which is why a normal distribution will not work, because if you look at a normal distribution, there will be values which would be above zero, but there would be certain values which would be below zero. So normal distribution is not appropriate to model prices because prices can never be negative. So then we need to hunt for a distribution which can be used for modeling purposes, which can probably model asset price. So instead of saying that price is normal, which is not possible normally distributed, let's assume that return is normally distributed. If we say that, theoretically it makes sense because there could be values above zero, there could be values below zero. Returns are permitted to have, theoretically, values way above zero, way below zero. So theoretically, it makes sense where returns could be normally distributed. Now, whether that really holds in the real world or not, that's a big question mark. But at least from a modeling perspective, instead of saying prices are normal, we will rather assume returns are normal. And we will work with that assumption. What are the features of a normal distribution? A normal distribution is typically symmetrical and unbounded, allowing for negative values. And most importantly, it will not allow asset prices to fall below zero. Yeah. So it becomes a much more realistic way to model financial assets. So the solution is to model prices with a distribution called as log normal distribution. Now here you can see two distributions. On the left is normal and the on the right is a right skewed distribution. It's called as a log normal distribution. So what is the difference between these two? Now if I assume returns to be normally distributed, the prices become log normally distributed. Okay. Uh, how is this possible? Let's look at the theory behind this. So we say that if, say we have two variables y and x, okay, and say y is equal to ln of x. Yeah. Now if we say that this y is equal to ln of x is, if we say is normally distributed, then by theory, x will be log normally distributed. Which is why when we talk about returns, which are normally distributed, now returns we know can be characterized in two formats. One is arithmetic return, the other is compounded returns or log returns. Arithmetic returns look like this: P1 minus P0 divided by P0. And log returns look like this: ln of P1 by P0. So this is a one period return, arithmetic and log returns. The second return which I've written here is assuming continuously compounded returns, which means compounding keeps on happening, where the frequency of compounding is theoretically infinite. So continuously compounded is the basic assumption here. And this is how returns can be put. So here we are saying returns which look like this, the log normal returns. If this is normally distributed, then the price is log normally distributed. Yeah. So which means that the prices, say stock prices or other asset prices, can be assumed to be modeled along a log normal distribution. Yeah. So that's a bit of a backdrop with regards to normal and log normal distribution and the fungibility of returns versus prices. This is very, very important, what I've just discussed. So always remember returns can be can have negative values. So returns will have or can be modeled as normal distribution. And since returns are written as ln of p1 by p0, um, p is log normally distributed or prices are log normally distributed. Yeah, so this is a bit of backdrop on this slide. And when I write R as ln of P1 by P0. And if I take, say, exponential on both sides, I get P1 is equal to P0 into e to the power R. If we extend for t periods, it looks like this. Pt is equal to P0 into e to the power RT. Yeah, just 1 second. Sorry. So essentially what we're saying is Pt is equal to P0 into e to the power RT. And that becomes the price or the future price at time period t. Yeah. So if I'm able to simulate R, I can find the price in the future, which is Pt is equal to P0 into e to the power RT. P0 will be known, T will be known, R can be simulated. And if R can be simulated or if R is known, then the price at time period T will also be known. This, please note, is assuming that returns are normally distributed. So the prices will then follow log normal distribution. Any questions on this so far?
No, sir.
Okay. Now, coming to the foundations or statistical foundations of the log normal model, the biggest advantage of log normal returns is that returns become additive. Okay, let's take a very simple example. So why we say that log returns are additive. So let's consider the return over 2 days, 0 to 1, 1 to 2. Prices are P0, P1, P2. Return, the log normal return over the first period, 0 to 1, can be written as Return 1 is equal to ln p1 by p0, and return 2 over 1 to 2 can be written as ln p2 by p1. Yeah. Can I say if I were to consider returns between 0 to 2, I would have written returns 0 to 2 as ln p2 by p0, right? So ending price divided by original price. Now I can realign this as p2 by p1 into p1 by p0, and then I can separate the two logs because log of a product is equal to the sum of logs, and this we know is nothing but return 0 to 1, and the other is return 1 to 2. Yeah. So return 0 to 2 is nothing but the summation of returns 0 to 1 and returns 1 to 2. We can, in fact, through induction, then go on to prove that return between 0 to n is the summation of returns I minus 1 to I. Yeah. So that's how it looks. So log returns are additive, and that is what is being mentioned here, additive returns. Also, a very key role of central limit theorem that even if short-term prices or returns rather are not perfectly normal, the central limit theorem implies that the sum will be approximately normally distributed. What does that mean? In fact, central limit theorem is an extremely important theorem which is borrowed a lot in finance, and hence a lot of modeling happens on normal distribution, especially assuming returns are normally distributed. These assumptions generally hold true in you know quieter, calm conditions or scenarios. But whenever there's stress in the markets, you should not assume returns are normally distributed. So in stress scenarios, we should consider distributions which are, you know, heavily negatively skewed, ideally, and which have or which are fat-tailed, which means the probability of seeing extreme tail events is higher than what normal distribution suggests, right? So the returns equal to normal distribution, usually for regular situations, regular scenarios, quieter, calm scenarios. But for stress situations, we generally we cannot assume this because returns will not be normally distributed. However, even if returns are not normally distributed over shorter periods, uh, even if that is true, if we keep collecting these returns and we see returns over longer periods, or when the sample size keeps on increasing, the returns might tend towards normal distribution. And that is because of the central limit theorem and the law of large numbers, which basically says that suppose you have a sample which looks like this. The sample is a limited sample. It could have a limited number of sample points, a finite number of sample points. Suppose from this, sorry, this is the population, and suppose you draw samples from this. You draw small samples from this, and you note their mean. Okay, so we note the mean x bar, and we keep redoing this exercise where we simulate a lot of different samples, and at the end of each exercise, we're going to just note what is the sample mean of each selected sample. If we keep doing this infinitely, the PDF or the probability distribution function of this sample mean becomes or tends to a normal distribution. So mu tends towards a normal distribution if the number of samples tends towards infinity or is very large. Yeah, so we keep repeating this experiment. Ultimately, we are going to get a normal distribution. So even if we start with a non-normal distribution, we could end up getting a normal distribution on the sampling mean distribution. And that is because of these properties of normal distribution where you keep on sampling, and over infinite number of samplings, this distribution of sampling mean will tend towards a normal distribution. Yeah. So that's exactly the role of central limit theorem. And that's what we, mean that if we are doing so many simulations, like thousands, lakhs, millions of simulations, then there's validity towards using normal distribution. Okay. So that's the crux of central limit theorem. And that's how it looks. So total return can be modeled as normally distributed. And if you invert that, or rather you take the log of that, you will end up, or you rather look at the price, you will end up getting the price as log normal distribution. So you start with the current price and you want to model uncertainty in the future. And a way to do that is using a simulation approach or a simulation model. Yeah. So all these are basically probabilistic paths that you can see. So a stock price can probably follow this path or this path or this path, and it will give us a range of possibilities in the future. So the question is, how do we do this and how do we generate these paths? So method one is to use the assumption of a distribution and generate futuristic paths based on those assumptions. And that is what is Monte Carlo simulation all about. So Monte Carlo simulation, you're going to specify the model, which means you're going to define the distribution of your asset price. So define asset price distribution, which essentially means that you need to define your asset return evolution, which means how does the asset return evolve. Second is, based on this distribution, you randomize the outcomes and you create random paths or generate random paths. And based on the outputs of the random paths, you analyze the results, create the distribution, and then probably the mean value will probably give you the price of the instrument in the future. You take the present value, that will fetch you the expected price of the instrument today. So this is what generally is done in the industry. So in a lot of places, Monte Carlo simulations is used. We will look at some of the specific examples where this could be used. So Monte Carlo simulation in practice, it's very heavily used to value complex options or derivatives which ideally do not have analytical solutions. For instance, if I want to value a path dependent option, for instance. Okay, so step back, what is a path dependent option? A path dependent option is basically an example of an exotic option which does not fall into the category of your long call, long put, short call, short put, right? It has different features which make it exotic. An example of path dependent option is Asian option. Yeah. So what is an Asian option? In an Asian option, you let the prices evolve over time, and then the option which is based on such an asset will have this characteristic. It will be max of average of STs minus K, comma 0. This will be the payoff function of a long Asian call option. Okay. It looks like max of average, which means it takes the prices at the end of every day, and say at the end of the month, if you were to find or if you were to calculate the payoff, it will take the average of all the realized ending values of the asset on this path, and you take the average of that. So that becomes the average stock price over the entire path minus the strike price, comma 0. So that defines the payoff of a long Asian call. Similarly, payoff of a long Asian put will be max of K minus average of ST, comma 0. So very similar to long call, right? Long call, the payoff we know is ST minus K, comma 0. And for a long put, it's max of K minus ST, comma 0. Long call is similar to buying the asset where the buying rate is fixed at the strike price. Long put is alternative to selling the asset where the selling price is fixed at K initially. So similar to that, we have payoffs of exotic options. Here we've taken the example of an Asian option, right? So this is how the payoff function looks like. Uh, Another example is look back option. Yeah. So it will, so suppose this is the path of the asset, and at maturity, the payoff of say look back call option will be equal to the max stock price achieved on the entire path minus K comma 0, which means it will see all the peaks. It will choose the peak, which is the highest, and it will choose that as the price here. Yeah, in the payoff. So this is the example of a look back call option, which takes the maximum or the highest value of the realized uh, asset price over a given period. So how would you simulate the values of these calls or puts exotic options? Today, how will you find the value today? So what we'll have to do is we'll have to simulate various paths, calculate the average payoffs, and then calculate the average of those values and then discount them back today. So that's where Monte Carlo simulations could be used. We'll go through the method very soon. Any questions on this?
No, no, sir.
Okay. All right. So let's go back here. So you need to specify the distribution. So how to put this into practice? Specify the distribution, generate random values, value the option, repeat and aggregate. Okay. So suppose let's take the example of an Asian call option, right? So how will you use Monte Carlo simulations to price this Asian call option? So for that, we have a starting value of the stock. Okay. Now, when we run simulations, this stock can take any path and typically will end up at maturity with the sum ending stock price. Yeah. And that is true for different paths. So in Monte Carlo simulations, you are going to model various kinds of paths. And for every path, we will have to calculate the average stock price, say on path one. Similarly, average stock price on path two, and so on and so forth. Once we have that, we feed that into a payoff function. And our payoff function is nothing but average stock price minus K comma 0, max of that. And then you calculate payoffs for each of the paths. Once you calculate the payoffs for each of the paths, you will have to eventually take the average of all these values, and that average will give you the future value of the Asian call option at maturity. But if I say what is the value today, so you need to discount this back or take the present value of that. So present value of the average of all these paths or payoffs is going to give me the price of the option today. So generally, when we take present value, we will use this formula, e to the power minus RT into your average is going to give you the value of the call option today. And this, we are talking about an Asian call option. Yeah, so this is a Monte Carlo simulation in practice. Any questions on this approach? Okay.
Yes, sir.
So let's take a step forward and let's look at some of the applications of Monte Carlo simulations. So Monte Carlo simulations is broadly used in the investment world and the risk world. It is used to value complex securities like options. I've just given you an example of exotic options like Asian options or look back options, where you can use Monte Carlo simulations to value these options. Okay. You can simulate future profits and losses from a trading strategy using Monte Carlo simulations and check if the out of sample in terms of simulations works or not for a particular trading strategy and how robust it is. You can calculate value at risk based on Monte Carlo simulations, and that method of VAR calculation is called as MCS value at risk. So MCS value at risk assumes that the asset price follows a certain distribution. Then we draw from these distributions, simulate the asset price, and then we calculate. We do that across various assets in our portfolio, calculate portfolio returns ultimately. So all these are, say, asset distributions, asset one distributions, asset two distributions. You'll ultimately create portfolio distribution, eventually portfolio return distribution, and then you'll calculate value at risk, which is nothing but the cutoff percentile in the left tail, or the maximum loss given a certain confidence level over a period of time is called as value at risk. So Monte Carlo simulations can be used to generate value at risk figures, especially for those assets wherein you want to generate future scenarios which have never been seen. A classical example of this is, suppose if I ask you, or if I tell you that you have a portfolio of high quality corporate bonds. Yeah. Suppose in this portfolio you have Reliance, you have Adani. Okay. Now, can I say that when I look at the historical prices or historical data of these bonds, first of all, they have never defaulted. So you will never have defaults. Okay, they have always made their payments. They have always made coupon payments on time, right? So there are no defaults in terms of principal or defaults in terms of coupons. But suppose if I tell you to calculate the default risk of my corporate bond portfolio. Now, can I say historically these have never happened? That Reliance or Adani bonds or AAA bonds of currently high quality companies have defaulted. There's no historical precedent for that. So how do we calculate default risk is a big question mark, right? So there we will utilize Monte Carlo simulations approach where we will assume a certain distribution for these corporate bond spreads or prices. After assuming this distribution, we're going to simulate rare events like uh, defaults or like rating downgrades. And then we are going to calculate what is the P&L out of these rare events, and then we are going to create a distribution of these P&Ls. And then the value at risk coming out from such a returns distribution is basically your MCS value at risk. And that's where Monte Carlo simulations is useful. By the way, this approach is popularly used in Basel 2.5 and 3. And this approach in Basel 2.5 and 3 in the regulatory documents is called as IRC, which is incremental risk charge. Okay. So this is not part of CFA, but I thought of giving you a bit of a background on how MCS is useful in terms of VAR. So in Basel 2.5 or 3, there is a component called as IRC, incremental risk charge, which uses Monte Carlo simulation approach in order to calculate value at risk. So here, what kind of risks are we capturing? We are capturing unknown or unseen risks. Like what? Like defaults and rating downgrades. Usually, a lot of times for high quality companies or bonds of high quality companies, there is no historical precedent of seeing defaults or seeing rating downgrades. Yeah, and which means that you would need to simulate such kind of outcomes using Monte Carlo simulation by using certain distributions, calculate P&L, take create the distribution of those P&Ls or returns, and then calculate the Monte Carlo simulation based value at risk. Yeah, so this is how it looks. So that's the application in risk management, and that is what we have written here. Yeah, it is used to simulate pension fund assets and liabilities to analyze funding gaps over time. So your assets and liabilities are going to fluctuate. And the difference between those, it's possible that sometimes the asset can fall below liability, creating a funding gap. So in order to simulate these funding gaps and I'll analyze these over a period of time, especially over stressed events, we could also use Monte Carlo simulations there. And also sometimes Monte Carlo simulations are used to value portfolio of assets which have non-normal return distribution. So there you need to use a fat tail distribution like a Pareto distribution or extreme value theorem or an F distribution or a mixture normal distribution or some other distribution which has fat tails, and that will lead you to, or a T distribution, and that could lead you to valuing assets which have non-normal return distributions. Yeah, so these are some of the applications of Monte Carlo simulations used in the industry. So that's the first method, which is futuristic. So generate futuristic parts. So that's the first point. And the second method, or the first method, the second method is using historical data. So there, that method is called as bootstrap resampling. What it does is you basically draw from these historical values, and what you do is you draw from it and you create a new simulated sample, and then you also do it with the replacement, which is you put it back into the pool and keep drawing this and create new simulated samples. So you can keep on doing this, and then you can find the average of all these values and use the approach the second part which was used in Monte Carlo simulations. But the key difference between Monte Carlo and bootstrap resampling is that Monte Carlo simulation is going to simulate future paths. Bootstrap resampling is only going to go back to your historical pool and randomly pick up some events, okay, or some returns, and that will help you create a new sample. So this is heavily based on prior history, method 2, but method 1 was based on futuristic values. Yeah, so this is the approach which is called as bootstrap resampling. So these are the two important methods. Any questions?
No, no, sir.
Okay, just a moment, please.
Excuse me, sir. Hello.
Yes, please tell me.
Sir, does Monte Carlo simulation also generate the probability of the path, uh, or only the path it is generating?
It generates values, prices, or risk.
Yeah. So, do I also get the probability of the stock following that path?
Generally, you're going to assume equal likelihood of all these paths.
Okay.
So whether stock is going here or going here or going here, the way Monte Carlo simulations work in finance is you're going to assume equal likelihood of all these paths and give them equal weightage into your payoff function. So when I say payoff on each path is this, okay? Can I say the
Yeah.
next step is to calculate expected value? So one way of calculating expected value is just take the average, and that's generally the case if millions of paths are done. But you can be, can you hear me?
Yes, sir.
But what can be done is uh, there are some weighted techniques in which probably you can give slightly higher weightage to paths which are somewhere close to the median and less probability attached to paths which are towards the extremes.
Okay, so
That is also
we assign
possible.
the weights to the paths, right?
Yeah, you can, but then you need to apply certain weights or probabilities to these. Okay.
Okay, sir.
But ultimately, the objective is not to calculate these probabilities. The objective is to calculate values or pricing of the instruments and use those
Right.
prices either to forecast future prices or to
Hmm.
forecast derivative prices or to forecast risk or to calculate value at risk, like I
Oh,
showed you
okay, sir.
in that example, in this example, sorry, this one, where we were using Monte Carlo simulation to capture value at risk.
Okay, sir.
Yeah.
Yeah.
Okay. Let's quickly look at this in Excel. Okay. We will not spend too much time, but I'll quickly take you through with some calculations in Excel of how do you run Monte Carlo simulation. Okay. For which we need to understand that, uh, see, first step in, okay, let's write down the steps, okay, in Monte Carlo simulation. Step number one will be to uh, specify the distribution of asset returns. Okay. Second would be to simulate values from these asset returns. Third will be to generate distribution. And fourth will be to calculate, say, the price or maybe risk, whatever is the end objective. Now, when I talk about specifying distribution of asset returns, one of the most commonly used ways is this. For that, I would just like to explain it using a short diagram. Suppose we start with asset price S0, and on the x-axis is time, evolution of time. We start with 0 to t. Yeah. So can I say that if I were assuming deterministic path of stock price evolution, which means a certain trend, a known deterministic trend, can I say the evolution of stock price will look like this? However, in the markets, a stock price never evolves like that. It looks like this, right? Which means there are always deviations away from the long-term average or the long-term mean. Now, this is called as the deterministic part, and the deviations from the mean is called as the stochastic part. So there are two sources of returns in a stock. Typically, I'm going to continue it here. So one source is deterministic, and the other source is stochastic. Okay, let's write it bigger here. Deterministic and stochastic. Now, can I say that the deterministic return is based on long-term growth rate? Suppose that rate is mu. Okay, so can I say that the deterministic return can be written as mu into S0? Now, can I say mu is what? Mean return, right? Mean return. Yeah. S0 is what? The deterministic. So what will mu into S give you? Please note mu is percentage and S says in dollar terms. So what will this give you? Say if I say a mean return is 10% over $100 stock. Okay, so can I say the mean is 10, right? So can I say ultimately I will get the return not in terms of percentage here, but in terms of what? In terms of change in the price of the asset. Please note, you're not getting returns here, you're getting change in the price of the asset. So there are two sources, one is deterministic and the other is stochastic. If you want delta S, okay, if you want return, obviously you will take delta S and divide by S0. Okay. But here we want changes in stock price because we're always interested in P&Ls or changes in the prices. Okay. Because that drives risk, that drives prices. So deterministic portion is mu into S0, but please note mu is over 1 year annualized. So what is an S0 is the current stock price. So can I say this will give me the annual change deterministically. I have to multiply that by what? A small change in time period. So what I do is, suppose I'm looking at valuing a 1 month stock option. I will create small buckets of time and call each of these DT. And what I will do is I will calculate this delta S over each small time period dt. So suppose this is delta S1, this is delta S2, this is delta S3, and so on and so forth. When I sum all these deltas and add them to the initial stock price, it will give me the final stock price. Okay. So in every time bucket, I'm going to run this equation, and this equation I've explained one part of it, which is take the annualized growth rate or the mean, multiply it by the asset price or the stock price, and that will fetch you the change, but over a year, deterministic change. So multiply by dt so that you get change in small time period dt. And then you add the stochastic part. Now, stochastic part of any distribution will be driven by what is my standard deviation. So imagine you have these two different distributions. One has a smaller standard deviation and the other one has a larger standard deviation. So can I say that ultimately whether the stock is changing by small amount or large amount will depend on what? Will depend on the level of sigma. Okay, so I should definitely have sigma volatility. This is in percentage terms. I will multiply this by what? By S0 again. And can I say this will give me what? Annualized one standard deviation movement. So suppose if I tell you 10% is the standard deviation of a stock of price 100, can I say annualize one standard deviation movement is what? 10. Yeah. Makes sense, right? If I assume sigma is 10% and assume S0 is 100, what is sigma into S0? Can I say 10? Now, what is this 10? 10 is nothing but annualized one standard deviation movement. Yeah. So first of all, my question uh, is this something which will be valid over a small time period? The answer is no, because this is for the entire year. So first of all, I'll have to scale the standard deviation to dt. And the way I do that is multiply it by root dt. And why did I do this? That's because when I scale uh, returns, I can just take the daily return and multiply it by time period. And I get a t-day return. We're talking about average returns. If I want to scale variances, I can take variances and I can scale them. So this is daily variance and this becomes essentially your T-day variance. But standard deviation is the square root of this. So if I want to work with daily standard deviation, and if I want to scale this, I will have to take root of time into sigma. And this becomes my T-day standard deviation, which is why in this equation here, we are multiplying by root of t, which is root of dt, because our time period is small time period dt. Yeah. So this will fetch us what? This is going to make it scale down to the standard deviation in a very small time period dt. And the next thing is, do we know how many standard deviation movements take place? Can I say this assumes, sigma assumes one standard deviation? But can I say, when I look at the evolution of a stock price, sometimes the standard deviation could be low, sometimes it could be large or high, sometimes it could be medium, sometimes it could be low. So, can I say the number of standard deviations itself changes or itself is unknown? When large standard deviation movements happen, that's when the stock or the asset prices will go through the roof up or will probably fall by too much. Yeah. And that's something which needs to be captured here. So hence we need to multiply this by Z. Z is what? Z is the number of standard deviation movements. So this is a classical example of a function, this one, which captures the change in a stock price or change in asset price. The first part, once again, deals with deterministic changes, long-term changes. That is a function of the mean. You multiply that by stock price, that will fetch you annualized deterministic change in the stock price, multiply by dt, that will fetch you the change over a small time period dt. That is the deterministic long-term trend. But can I say the stock is moving randomly or stochastically, and we need to add a stochastic portion to it? There we start with one standard deviation in percentage, multiply by S, that will fetch you annualized one standard deviation movement over a year. Scale it down to dt, so multiply by root dt, and then eventually also multiply it by Z, which captures the number of standard deviation movements. And basically Z follows a normal distribution 0 to 1, which means it has mean 0 and variance 1. Okay, so it's nothing but an outcome of standard normal distribution. Any questions before I close today's session?
No, sir.
Okay, now we still haven't done the simulations. Next session, I will probably start with simulations and then go to the next reading. Yeah,
Yeah.
make sense? Okay.
Yes.
All right. So this
Yes,
was
sir.
reading 6. Please go through it. What I will do is, Sarthak, it will take probably a few days to send it across to you, the books. I will send you the soft copy of the text. Okay. So at least you can start reading the
Okay.
chapter. Yeah.
Okay. Excuse me, sir. Could you
Yes.
explain once again the Z part? I did not. It's not
Which
clear yet.
part?
What is Z?
Z is the number of standard deviation movements. Okay. Let's take a step back. Good question. Z. Now, can I say we have done the Z value in stats? What is
Yeah.
the Z value in stats? X minus mu by sigma, right?
Yes, sir.
What does this capture? Can I say this
Uh,
captures a normalized deviation
yes, sir.
from mean?
Yeah.
Yeah. So Z is capturing normalized deviation from mean. So what if I say this value is -1? How do I read it? It means
My
it's a
value
negative
is,
one standard deviation movement from the mean.
yeah.
Correct. That's how I read the value of Z as -1, right?
Yeah.
Similarly, if I say Z is plus 1.6, can I say that is plus 1.6 standard deviation up movement from the mean, correct?
Yes, sir.
So that's what the z value is which we are borrowing. We are borrowing it from the standard normal distribution. So when I look at this distribution, yeah,
Hmm.
on the x-axis is the z value. On the y-axis, obviously, is probability, PDF this is. Now, the z value can range ideally from, I mean, theoretically from minus infinity to plus infinity, right? But the
Yeah.
probability as soon as we go to a -3 standard deviation is extremely low. If this is a normal
Hmm.
distribution, same is the case for +3 standard deviation. But any value which you see here in this standard normal distribution is what
Right.
called as a z value. Now, this is the z value which we are going to use in our equation, which is delta S, or rather ds if you're taking stochastic processes, ds as mu s dt plus sigma s root dt into z. This is the z value which we are taking. Okay, so that defines the number of standard deviation movement. Yeah, and the question should be, how do we even get this? Yeah, so for that,
Yeah.
what we do is we create a CDF, cumulative density function. Yeah. In
Okay.
cumulative, can
Yeah.
I say it varies from 0 to 1, the probability?
Yes, sir.
Okay. And in Excel, there's a function called as rand function. Even in Python, random is there. You can
Yeah.
use np.rand, random.rand. Yeah. So that will fetch you random numbers between 0 and 1, for instance. And how can you use that? So once you generate random numbers between 0 and 1, you assume that to be cumulative probability. On the y-axis is cumulative probability. On the x-axis here is the z value. So if
Right.
suppose the value is zero point 0.1 and suppose I invert that value and get the corresponding z value. Please note this is y and this is x, right? So I would need
Hmm.
to invert this zero point 0.1, which is y value, and get the corresponding x value, which is nothing but z, which is number of standard deviations. Yeah.
Right.
And
Yeah.
this inversion is possible through a function which is called as norms inverse function in Excel. So we are inverting the standard normal distribution, and from probability, we are arriving at the z value. So basically, we are saying, okay, probability 0.1, what is the z value
Right.
corresponding to that zero point 0.1 probability?
Right.
Yeah. So
Yeah.
next time we are going to use this, and we're going to calculate Monte Carlo simulations or work out
So,
Monte Carlo simulations.
but the time period we are taking is DT, which is a very short period of time, and
Yeah.
we cannot really assume that the stochastic path will take a normal distribution for a very short period of time. So that was my doubt. How can we assume a normal distribution there?
We can. So suppose theoretically, suppose it's you are say valuing a 1 month option, and suppose your time period is 1 second.
Right.
Okay. Now every 1 second, if you take, can I say there will be a lot of 1 second time periods, right? So ultimately, this will tend towards a normal distribution. So the further you subdivide or smaller the dt, the more it tends towards normal distribution. But yes, if you take 1 day, can I say there will only be 22 trading days in a month? Yeah.
Yeah.
Versus if you take 1 second, can I say there would be, lakhs of these values, probably even, more than lakhs. And that would mean that you are safe in terms of assuming normal distribution. So the smaller the subdivision of your time period, the more you tend towards normal distribution.
Right.
Yeah. So your answer will be more accurate towards the normal distributed value. And hence, what we need to do when we run Monte Carlo simulations is we run ideally millions of simulations so that the various paths are, kind of negated, and you end up getting something close to normal distribution, which is why so many paths are simulated across Monte Carlo simulations. So two ways in which you can make simulations useful. or pertinent
Mhm.
is one, okay, effectiveness of Monte Carlo simulations is dependent on two things. One is number of simulations. Higher the number of simulations, the better. And
Right.
second is the interval of time. Lower the interval of time, the better.
Okay, sir.
Yeah.
Yeah.
So that's on the effectiveness of MCS. We will continue this session next time and we will try to see how to actually run simulations and then go on to the next reading. Yeah, so very interesting topic this was on Monte Carlo simulations, log normal returns, and bootstrap resampling method. So once again, MCS is doing futuristic simulations. Bootstrap resampling is taking simulations from past values, right? So this is more pertinent if you want to model uncertainty, which we don't know what it will be in the future. Yeah.
Right.
Thank you so much.
Thank you, sir.
Take care.
Good night.
Good night.